Hello everyone and welcome back to Total Organic Chemistry. This video I'm going to be taking a look at meso compounds as well as chiral resolution or resolution of enantiomers. Hopefully by the end of this video, the questions that you'll be able to answer are what are meso compounds? How do I recognize meso compounds? How can I synthesize a set of diastereomers? And finally, what are some methods that I can use to separate two enantiomers? And if you need any review on stereochemistry or properties of enantiomers, I would highly recommend subscribing to my channel and taking a look at a few of the previous videos that I've uploaded on those topics. So we can start off with meso compounds here. I'll start by drawing a substituted butane molecule. So we have maybe a chlorine and a bromine substituent on the same side. This is the Fischer projection. And we can also draw the mirror image of this Fischer projection with, again, the chlorine and bromine substituents, but on the opposite side. And if you remember from learning about Fischer projections, the mirror image of a Fischer projection is the enantiomer. So these two compounds are indeed enantiomers, as you would expect. However, what if we draw the same sort of skeleton, except now we have two bromine substituents on the same side? Well, we can again draw the mirror image of that Fischer projection with the bromines on the other side of the molecule. But you can also notice that these two molecules are actually the same. If you rotate the first one by 180 degrees, you'll end up with the second Fischer projection. And again, if you remember from Fischer projections, 180-degree rotations result in this same molecule. So what's interesting is that these molecules are actually the same one, even though they are mirror images. And that is because we have this plane of symmetry. Because the molecule is symmetrical, we have the same substituent on carbons 2 and 3 here. That is what we call a meso compound. So it has two stereocenters, but it is symmetrical, which means that it does not have an enantiomer. So, as a definition, meso compounds are compounds with more than one stereocenter, but that also have a plane of symmetry. So that's important to recognize whenever you have compounds with multiple stereocenters. If I start a new page here, we can also have maybe this substituted cyclobutane, so a cyclic compound, our four-membered ring. And let's draw the two bromine substituents trans to each other. So one will be facing towards us, the other away from us. Again, as with the last one, these two compounds are enantiomers. They are mirror images, and they are non-superimposable. Remember, there is no plane of symmetry in this molecule. However, if we draw the same cyclobutane skeleton, except now we have the bromine substituents cis to each other. So remember, cis is the same side. And maybe we could consider drawing the mirror image with both of the bromines pointing into the page. But if you think about this for a second, these are actually the same molecule again, because you can just flip that molecule over and end up with the first one. So they are superimposable, which means that again, this second cyclobutane molecule that I've drawn is meso. So it has a plane of symmetry, and it has multiple stereocenters, which means that it does not have an enantiomer. So to reiterate, if you ever have a molecule with more than one stereocenter, it's always a good idea to look to see if you can find a plane of symmetry in that molecule, which will signify that it's a meso compound, and it actually is achiral. So it's not optically active, and it does not possess an enantiomer. So the second topic I'd like to take a look at in this video is chiral resolution, or resolution of enantiomers. So basically these are a set of methods that chemists use to separate a racemic mixture. So racemic being an equal mix of two enantiomers. And all of these methods rely on the fact that diastereomers have different physical and chemical properties, whereas enantiomers have almost exactly the same physical and chemical properties. So our goal in all of these is to make a diastereomer, separate it, and then recover our enantiomers separately. So the first of these methods is called recrystallization. And what recrystallization is synthesizing a chiral salt out of, first we have a racemic mixture, so let's say A plus B, and an enantiomerically pure compound C, for example. So we only have one enantiomer of C. If we form a salt out of those compounds, then what we get is a mixture of diastereomers, say AC and BC. Like I said, those diastereomers will have different physical properties, so it's much easier to separate them using conventional means. We can separate them and then decompose the salt into its constituents, which will yield us the pure enantiomers A and B separately. Another method is esterification, and this is a reaction that we'll talk about later in the course, but it involves making an ester, so an organic ester, out of a carboxylic acid and an alcohol. So, for example, if we have a racemic mixture of alcohols, let's call them RaOH and RbOH, where R is our chiral group, and an enantiomerically pure carboxylic acid, we'll call that R' with a carboxyl group on the end. And if we convert these into an ester, then again, like the last one, we get a mixture of diastereomers, so a diastereomeric mixture of esters, which we can then separate fairly easily, decompose the ester back into its constituents, and recover, now separated, the chiral compounds with the groups Ra and Rb. The last method I'll talk about is chromatography. So if you've never had a course on chromatography before, or you've never learned anything about it, basically chromatography is a method where we fill a column with what we call a stationary phase, then we insert our sample into the column, and based on the interactions between our sample and whatever is in the stationary phase, different constituents of our sample will come out of the column at different times, so we can separate a mixture of compounds. In terms of chiral resolution, what we can do is have our stationary phase be an enantiomerically pure compound, just like we've had in the other two methods. Then we insert our sample, so our racemic mixture of A and B, into the column, and because our stationary phase is chiral, it will react differently with the two enantiomers in our mixture. So therefore, our enantiomers will come out of the column at different times, and we can separate them. So one question you might have is, how do we get those enantiomerically pure compounds in the first place in order to separate our mixtures? Well, we actually get them from nature. Nature is incredibly good at manufacturing single enantiomers of proteins or sugars or anything like that. And because of that, we can often extract single enantiomers of compounds from plants. So for example, some of those single enantiomer substances that we can get are tartaric acid and cellulose. So thank you again for tuning in to Total Organic Chemistry. As always, please be sure to like and subscribe to my channel for more videos like this. And please consider donating to my Patreon page, which I will link in the description. As I always say, it really helps me continue creating content for all of you. I will see you in the next video.